Hi everyone, welcome to recitation 20 on block processing. My name is Sophia. As you will see throughout this course, building neural net models can quickly become a tangled mess, especially if you decide to take an unstructured approach. In this recitation, we will go over concepts of layers, blocks, and some tools that PyTorch provides can help you simplify your workflow, make your code more reusable, and manage complexity more effectively. So we're going to first talk about a concept called modularization. Modularizing a neural network is conceptually very similar to using classes in object-oriented programming. In object-oriented programming, we will define reusable structures, for example, classes, to encapsulate functions, variables, parameters. Similarly, in PyTorch, when we're using nn.Module, we can subclass to encapsulate combinations of layers and logic. Just like a class would have attributes and methods, a PyTorch block can have submodules and forward methods to define such behavior. This designing methodology would allows you to reuse blocks, extend them, and build hierarchical models the same way that you would build complex programs with classes and inheritance. So visualizing what we just explained, if we're starting from the leftmost, this is like a tangled class. This is like a tangled network structure where we have neurons and the way that we were like transfer the arrows when we're like transferring the computations. We can put that into encapsulation and then further extend that into a hierarchical structure where each smaller block would do a certain amount of part of explanation in the neural net, and then putting it together, it resembles the same structure as the one on the left. So they do the same thing, but they have a very clear way of flow, and it's easier to maintain, easier to reuse, and they're less likely that you will change like one part of the code that like affect the entire thing when you have to redo everything over. All right, hopefully this makes sense. And then let's talk about some basic building blocks and structures of doing such modularization. So let's start with layer. What is a layer? Layer is an atomic computation unit in the neural net. You can think of it as like the very basic building block of a neural net. It takes input sensors, applies computation, return output sensors, and then also have learnable parameters, which are optimized to meet a given objective. What is a simple neural network could often consist of an input layer, some hidden layers, and an output layer. We will talk about that more in the class. So a block, on the other hand, it's like a logical grouping of layers that works together to achieve a simple task. Blocks can represent a single layer, a set of layers, or even an entire model. These blocks can be combined recursively into larger, more complex structures. Why do we use them? This modular approach makes things easier to manage and understand. You can focus on a single chunk instead of the entire model. That also simplifies debugging, allow you to modify parts of your model easily, and also helps with scaling. So let's take a look at some code to so that as a better explanation or visualization to show what we just discussed. Okay, the first one, these are like imports and installations. All right, it works. And then let's look at this very simple CNN classifier. So this is a simple classifier, has two convolutional layers and two fully connected layers. As we can see, it is designed literally layer by layer. So there's convolutional 1, batch norm 1, convolutional comp2d2, and then batch norm 2, fully connected layer, and then the forward method. Well, we can see the repetitivity over here. Like we can possibly thinking from like a class or object-oriented programming perspective, there are certain, sounds like, or intuitively, there will be ways that we can take the reusable functionality out and then define maybe a function to that. let's move forward and look at how we can do that in PyTorch. So this is a package called nn.Sequential. It is a class. We will inherit from this, like make sure you import that when you write your code. Let's look at this one. Right now, we have an init function that defines self and conv block 1, where in a sequential of layers, each of this block, each of the convolutional blocks have a conv2d layer, a batch norm, and a relu activation function. Now, at conv block 2, there is also the same repeated structure again. After that, we have a decoder that consists of the fully connected linear layers, which later maps the output out into the number of classes, and also a sigmoid function. Now we have forward that puts the above structures together. All right, then we look at the summary. Now, instead of the layer by layer structure, we have a hierarchical one now. It has sequential, the first one. This first one has conv2d batch norm, relu, conv2d batch norm, relu, and then the last one is linear, sigmoid, and linear. Exactly, it does the exact same functionality as the first layer by layer structure, but it is easier to maintain and reusable when we're trying to take like one block out or make modification about a single block instead of changing the whole thing. This is much better, but still not perfect. Did you notice that self.conv block 1 and self.conv block 2 looks exactly the same? Can we do something about it? We can define a function, right? It takes an input, it takes several inputs, returns this sequence of conv2d batch norm and relu function. Now, when we call this conv block function, we can further simplify our code and make it easier to maintain. Now we can just change the function itself, and everything in this class, in this init function, will be changed connectively. Again, this is a even more this is a like an even more simplified way of defining this convolutional CNN classifier as comparing with the previous one. We define the function that does the exact same thing. All right. So it's cleaner now. Still, convolutional block 1 and block 2 looks almost the same. We can do away with another conv block function that merged them using nn.Sequential. What do we mean by that? So we are defining a variable called encoder, where it is a sequential class that has these two convolutional blocks, which used to be conv block 1 and conv block 2 over here. So we put another layer, or we put another like hierarchical layer above that. Now it is an encoder. Okay, we have an encoder and a decoder. Inside this encoder, this sequential of two convolutional blocks, which are does the same functionality again, but look how the structure of the class has changed, the structure of the network. So we have two sequential classes at this level. This is our encoder. This is our decoder. Inside the encoder, we have two blocks. The first is conv2d, batch norm 2d. Another block does the same thing, conv2d, batch norm, and relu. This is encoder, this is decoder. Feel free to refer to the code and go over, like, visualize this structure. Okay, now we know how to do the very basic ones to create hierarchical structure in the neural net. There is another thing that we should talk about, that is dynamic sequential, when we can create multiple layers at once. So dynamic sequential refers to a way of building the sequence of layers programmatically with loop or logic. Think about this as a for loop. Like if you want to create multiple layers, if you want to create multiple like layers at once, you use a for loop to do that. If I want to multiply or like it's doing the repetitive things over and over again, but it's like inside the loop, right? So we can do that programmatically with code or logic rather than hard coding each one manually. In PyTorch, it usually means that creating a sequential block where the number of layers, their configurations or types are determined dynamically at runtime based on some condition or loop. For example, let's look at this self-encoder. The variables are might be different as we're going through each layer. Would it be nice that if we can define the size as an array and automatically create all the layers without writing each one of them? Fortunately, we can create an array and pass it along to sequential. So here we're zipping all the stops where the shortest list is executed. We have convolution of blocks where we create all those number of blocks that we need, and we pass along the conv blocks into encoder. And then we have to keep the same decoder along the way, have the same forward function. And here is how we are creating the same thing, but right now using a loop, or we call it dynamic sequencing over here. All right, it has the same functionality as we did over and over again over here. If you want to look at the input feature and output feature, number of them, so we can print those, and it shows exactly what we need, 32 and 64, the same as the ones that we look at over here. Conv block 1 and conv block 2. All right. Now, if we just want to add a size, we can easily add a new number to the list. This is a common practice. So let's look at what changed here. We add another block over here. And instead of 64, we have 1 to 8 as in the shape as for now. So we added another block of code, which are like have the same structure with the previous one, but instead of creating it layer by layer, we're doing it in a dynamic dynamic creation that's almost similar as a loop. Again, pass along the conv blocks here and create that decoder forward function. We can do the same thing for decoder. So create convolutional blocks in this definition, pass it on into encoder. That's what we just did. We can also create decoder blocks, create those, pass along into decoder. And then we define this last for the output layer. Now forward, it's the exact same thing. Now we have more layers, more blocks in the decoder over here. So it's still the same thing, linear, sigmoid. And at the output layer, we have the last linear. We can make things even more modular by splitting the encoder and decoder into separate classes. So we can create a class that is an encoder. We define the blocks, convolutional blocks, using sequential function, pass along the function that needs that and the parameters, define the forward function, we can create a decoder with that, and then put it together in this simple CNN classifier. I have encoder, decoder, forward function. Let's run that. Notice that we have an increasing parameter because we have added another block of 128 over there. By dividing our modules into submodules, it is easier to share the code, debug, and test it. So we break down from the beginning that when we have layer by layer structure for this neural net, we break those down into a much cleaner and easier to maintain structure that is like a class. See it changed over here. I have decoder and encoder and decoder now. Cool. The next concept that we're going to touch base is ModuleList. So ModuleList allows you to store the module as a list. It can be useful when you need to iterate through layers and store more information. The main difference between sequential is that ModuleList does not have a forward method, so the inner layers are not connected. Assuming we need each output for each layer in the decoder. In the decoder, we can store it by running this part of the code. We can store the trace in model.shape. We'll create this model, save it, and then run this trace. Another useful structure is module dictionary, where we need to choose. Module dictionary allows you to store it as like the name defined, like it's sorted like a dictionary. It can be useful when you need to choose a module based on some condition. But what if we want to switch from leaky ReLU in our convolutional block instead of ReLU? We can use modular dictionary to create that for the module and dynamically switch when we want. So in the activations, we can create the name like leaky ReLU. This means we're using this function. ReLU means we're using the regular ReLU function. And in the sequential, we can pass along the activation as we need. So here, when printing this block, we're passing along the parameters and another one called activation, where we have defined in this convolutional block function where we can choose which activation we're using. So putting it all together, we're defining a convolutional block, returning which returns a sequential of comp2d, batch norm, and activation. We have a decoder block that has linear and sigmoid. We have our encoder, our decoder as classes. We define the sizes and we pass along those blocks. We use those functions that we just created. Now we put the class together. We have our encoder, have our decoder, which each defined previously, and then we have the forward function. Now it becomes a complete class. So in summary, we have seen now how to create a modular neural network using nn.Module, nn.Sequential, ModuleList, or mod dictionary. Using module when you have a big block composed of like multiple smaller blocks. Use sequential when you want to create the small blocks from layers. Use list when you need to iterate through some layers. Use dictionary when you need to choose, for example, in the activation function. For more information, please check out the official documentation. We have attached the link there. Thank you for being here. Thank you for listening. Best of luck for the semester.